Good afternoon, class. We are looking at Chapter 5, Integrals, 5.1 to 5.3, the Fundamental Theorem of Calculus, or FTC. Here's the second part. And so what we did is the following. According to FTC, where f is continuous in a closed interval of a to b, the derivative d dx of a, the integral of a to x f of t dt is f of x. In other words, the derivative of the integral gives you the function at the upper limit back. Given capital F prime of x equals f of x, the integral of a to b f of x dx is f of b minus f of a. This is called a definite integral, which is a number. So now, the definite integral of 1 to 2, 4v to the power of 6 minus 3v cubed over v cubed. We get this ready by making up two fractions. The first one is 4v cubed. The second one is simply minus 3. And we are going to use the power rule. So this becomes v to the power of 4. This becomes negative 3v. And we plug in the upper limit and lower limit. This is the only calculus step. So plug in 2 and then plug in 1. When we plug in 2, we get 2 to the power of 4 minus 3 times 2. When we plug in 1, we get 1 to the power of 4 minus 3 times 1, which is 16 minus 6. So that's 10. 1 minus 3, that's negative 2. This makes it positive, and the result is 12. So the first bracket results in 10. The second one, negative 2. This negative makes it positive. They add up to 12. In this case, if you recall, we did it in the previous section by cutting it into 3 fractions. This one is 1 minus 7 over x plus 2 over x squared. You can see it in the previous section. So we rewrite 7 over x as 7 times 1 over x with the sign minus 7, and 2 over x squared as 2 over x to the power of minus 2. So we can see, since this is dx, this gives you x, this gives you minus 7 ln x, and this one, using the power rule, again, I'm going to remind you how I did that before. So 2 over negative 2 plus 1, x to the power of negative 2 plus 1, which simplifies to negative 2 over x, and evaluate it from 1 to 3. Again, you can find this in the previous note. In the previous note, we had a constant. We don't need a constant here because this is a definite integral. So plug in number 3, plug in number 1, and evaluate. When we plug in number 3, we get 3 minus 7, ln 3 minus 2 over 3. Minus, when we plug in 1, we get 1 minus 7, ln 1 minus 2 over 1. We are going to keep the first brackets intact. ln 1 is 0, so this is 0. 1 and negative 2 gives us negative 1. This negative makes it positive. Again, the first brackets we are not changing. 3 and 1, they add up to 4 minus 2/3, and 4 is 12/3. We get 10/3 minus 7 ln 3, which is an exact answer. Always keep it as exact unless you've been asked to change. The integral of 0 to power 2, 1 plus cosine t dt. Again, this was done. But we didn't have this part. So the independent variable is t. So 1 becomes t, cosine becomes sine. And by the way, remember the derivative of cosine is negative, but the integral is positive. And we are going to evaluate this at pi over 2, meaning plug in, and then at 0, meaning plug in, and look at the difference according to this, f of b minus f of b. Of course, 0 is 0, so it's sine of 0. So this goes to 0. Now sine of pi over 2 is 1. And again, we keep it as an exact answer. That's why we don't change this. Always exact answer, unless they ask you for decimal representation, in which case they ask you how to do the round. How many decimals? Another example which was done, and now we are going to do with the definite integral resulting in a number. So we need to make some changes to make this doable. Square root of x is x to the power 1/2. So we have 5 times x to the power 1/2. X has the exponent 1. 1 and 1/2, that's 5x to the power of 3/2 plus 3x to the power 1/2. The reason we do it this way, because we want to make it ready for integration. Each case uses the same power. So starting with the first one, 5 divided by 3/2 plus 1, x to the power of 3/2 plus 1. Second piece, 3 divided by 1/2 plus 1, x to the power of 1/2 plus 1, and of course, from 1 to 4, from 1 to 4. And believe it or not, this is the end of calculus. Now, we are going to simplify this number. We get 5/2 here, which means this is 2. We get 3/2 here, which means this is also 2. So 2x to the power of 5/2 plus 2x to the power of 3/2, evaluated from 1 to 4. We plug in 4 first and then 1. Let's evaluate. 4 to the power of 5/2 means the square root of 4, which is 2 to the power of 5, which is 32. So you have 64 here. 4 to the power of 3/2 means the square root of 4, again 2, cubed means 8. 2 times that makes it 16. 1 to the power of 5/2, 3/2, 2/3, it's just 1. So this entire thing is 4, so we have minus 4. So 64 minus 4 is 60, which 16 becomes 76. That's the final answer. Application problem, example 7. Water flows from the bottom of a storage tank at a rate of R of t equals 200 minus 4t liters per minute. Find the amount of water that flows from the tank during the first 10 minutes. So the moment you hear rate in calculus, it's referring to differentiation. So if capital R of t represents the amount of water that flows from the tank at time t, then the rate of flow is given as capital R prime of t equals lowercase r of t equals 200 minus 40. So the amount of water follows what we call a net change theorem. So the amount of water that flows from the tank follows the integral of a to b f of x dx, which is capital F of b minus f of a, is also known as accumulated change or net change theorem. So for the first 10 minutes, a to b would be 0 to 10. F of x dx is the rate 200 minus 4t dt. So the integral of a to b r of t dt. So the integral of 0 to 10, 200 minus 4t dt. So we went over all this explanation to mention this is an application problem following this theorem, net change theorem or accumulated change theorem. So this becomes 200t, this becomes minus 2t squared, that shouldn't be a big deal. You plug in 10, you plug in 0. So obviously 0 makes it 0. When you plug in 10, this is 2000 minus 200 gives you 1800. As far as the units, if you go back to the rate is liters per minute. So this is the amount, so it must be in liters. So 1800 liters. Many fish, example 8, grow in a way that is described by the von Bertalanffy growth equation. For a fish that starts life with a length of 1 centimeter and has a maximum length of 30 centimeters, the equation predicts that the growth rate is 29 e to the power minus x centimeters per year. Where x is the age of the fish, how long will the fish be after 4 years? And round your answer to 1 decimal. By the way, this itself has been experimentally found and it's an approximation. That's why they want so many decimals. And you always go with more than what is given to make a decision on one. So you minimum need one more decimal. Okay, so always go with 2 decimals. I normally go with more, but then I will follow that. Now, what do we have here? We have a similar situation. If L of x represents the length of fish, that's what we're looking for. How long is the fish? At a general age of x, then the growth rate is its derivative. L prime or dl dx is this. What is this? The initial value. L of 0 equals 1 centimeter. So there are 2 ways to solve it, and we're going to do it both ways. First, the amount of increase follows the net change theorem, would be the integral of f of x dx. In this case is 29 e to the power minus x times dx from a to b, because we want the first 4, 0 to 4. First 4, 0 to 4. The derivative integration is the same because you're multiplying by -1 or dividing by -1 makes no difference. You get -29. Of course, you're dividing. And you plug in 4, you plug in 0, you can take the -29 out. E to the power of 0 is 1. However, makes no difference because this one we don't know. We use a calculator times -29. And I'm going to put a bunch of this. So that's the amount of increase. The fish starts life to be 1 centimeter. So that's the starting point. Then when the fish is 4 years old, is the sum of these two numbers because this is the amount of increase. And I get 29.4688. Then I need 1 decimal, everybody. I want 4, next to it is 6, goes up to 5, roughly 29.5 centimeters. So that's one way to do it. If the question has several parts and wants the length of the fish at different time, such as 2 years old, 3 years old, 5 years old, 7 years old, it's better to find L of x in general. So if I integrate this without the limits, then it gives me the same answer as I have here plus a constant. And of course, so this is the answer, and it's an initial value problem because L of 0 is given, which means I can use this to find the missing constant. This is a family of functions. With this one, I get one particular function. So having said that, we are going to replace the x with 0. Minus 29 e to the power minus 0 plus is 1. And e to the power minus 0 or 0 makes no difference. This is 1. So if this is 1, this is -29. And the constant becomes 30. So L of x is -29 e to the power minus x plus 10. So for a 4-year-old fish, you have to put the x as 4. And as you can see, it's identical to what we found here. Of course, we do the rounding. And the point being, when you find this, if the question has part B, let's say, 5 years old, 2 years old, 3 years old, all you have to do right here into this formula, replace the x with that number. So that's the advantage of having the L of x in general, because otherwise you have to go through this process again.